Hi there, my name is Scott Bozeman. I'm a PhD student at Oregon State University, and I'm going to be talking about controlling chemical composition in simultaneous wire powder fed directed energy deposition for fabricating functionally graded materials. So functionally graded materials are of interest to a lot of demanding applications. And this is where you have one alloy and create a gradient between another alloy. This is similar to a bimetallic structure or a dissimilar metal weld, except this gradient between the two materials greatly increases their material compatibility. Making functionally graded materials with metal additive manufacturing lets us program parts with site-dependent properties. So for instance, we can have an alloy that is very corrosion resistant, maybe on the surface of a part, and use a cheaper or stronger alloy in the bulk, whatever your application needs. One of the big challenges, though, of functionally graded materials is getting mixing in this gradient, because we want our gradient to achieve our desired compositions and desired properties. So I'm going to be talking about this mixing today. So functionally graded materials are typically fabricated with directed energy deposition. In DED, you can either feed in wire or you can blow powder and it's melted by a heat source, in our case, lasers. You can have multiple feed wires, multiple powder hoppers to achieve the composition gradation. Or in our case, we're using one wire and one powder. You can see here in our little video, we're extruding wire. All of that wire enters that melt pool. However, the powder, when that's blown, the powder, some of that goes in the melt pool, but a lot of that is blown off or misses the melt pool, is reflected off. And so it can be kind of challenging to calibrate the compositions when we don't know exactly how much powder is going into the melt pool. And so we're trying to study that. We're looking at using 309 stainless steel wire and pure iron powder for a simple study because we know these materials can mix together well. We're looking at the effects of wire and powder feed rate. So we have 5 wire feed rates and 5 powder feed rates. And then we held all of our other laser parameters constant. 309 stainless steel has 23% chrome. And so when we add more iron powder, this amount of chromium will go down and the amount of iron will go up in our structure. And so we're doing this by approximating the bead shape as a half-ellipse. So in our bulk wire and powder structure, we can measure the height easily, measure the width. That takes just a few minutes after we've printed the structures. And we can estimate it as an ellipse and get the area. Then, since we know the area of just depositing the wire, because we know exactly how much wire we fed based on our wire diameter and how much the length of wire we fed, then we can take the ratio of those, the area of the wire divided by the area of our wire powder structure, and multiply by the composition of our feed materials to estimate the composition of our wire powder bulk structure. And so, for instance, this could be the amount of chrome would be based on the ratio between the two and the amount of chromium in the wire, the amount of chromium in the powder. So when we made these, looking at our wire feed rate and powder feed rate, we did notice that our high powder feed rates weren't very good. We had these big gaps between, so these don't adhere to a very, half hemisphere shape. And we also noticed we have macrosegregation. So these are unmelted iron powder particles. And we also have some segregation here where we have a lighter gray and a darker gray region. Now at our lower feed rates, we do see that, yeah, we have good mixing. And this is proved by EDS measurements on the next slide. And the shape looks semi-elliptical, which is good and fits well too. So doing EDS, we noticed that at the bottom, this lighter gray region is very chromium rich or very stainless steel wire rich. You'll see these downward triangles here. They're up close to 23% chrome. And so this is showing we do have some macrosegregation in some of our samples. But again, the lower feed rate ones are all very close. We're getting good mixing here, and they are close to our targets, the squares. So overall, we're within 20% for all 25 samples. For our predictions. So this is a very easy way to estimate our compositions. We do notice this downward trend, and we can attribute the high powder feed rates to centered powder on the bead surface, as well as that non-semi-elliptical shape. But overall, this is a good start, and we're looking at fabricating larger wire powder DED graded structures in the future, specifically looking at the bead overlap and our grading or composition strategy as important parameters. So I really want to thank you for attending my talk today. You can access me by email, ask any questions, and connect with me. We'd also like to thank DOE and Packway for supporting this work and funding us. Thank you. Have a great day.